All right, let's jump right in. Today, we're not just doing math, we're playing detective. We've got a case on our hands, a system of equations with a really mysterious parameter, all happening in this weird world with its own strange set of rules. So, let's grab our magnifying glasses and get to the bottom of this thing.
Okay, so here's our game plan. Think of this as our investigative roadmap. We'll look at the case file, check out the crime scene, talk to our key witness, you get the idea. We'll identify the suspects, and then, finally, bring it all home for the final verdict. Let's do it.
First things first, every good investigation starts with the case file, right? So let's open it up.
And here it is. This is the heart of our mystery. We've got this system of equations, and see that little parameter a in there? That little guy can change everything. And to make things even weirder, this whole thing is happening in a place called z sub 7. Our job? Figure out for which values of a this system gives us one solution, no solution, or a whole bunch of them.
Okay, before we just dive in and start crunching numbers, we have to understand the crime scene. This isn't the number system you and I use every day. We gotta learn the local rules, the laws of this strange land. So this crime scene is what mathematicians call the field z sub 7. And you're probably thinking, what on earth is that? Well, imagine a world with only 7 numbers. 0, 1, 2, 3, 4, 5, and 6. That's it. Anytime you do math and the answer is 7 or bigger, it just wraps around. It's kind of weird, but there's a really simple way to think about it. Think about a clock, but instead of 12 hours, this clock only has 7, numbered 0 through 6. So if you're at hour 5 and you add 3 hours, where do you end up? You don't go to 8, because there is no 8. You go 6, then 0, then 1. You land on 1. That's it. That's modular arithmetic. So in this world, 5 plus 3 equals 1. And that one simple idea, it's absolutely crucial for cracking this case. All right, in pretty much any case involving a system of equations, there's always one key witness, the one that can tell you almost everything you need to know. And in our case, that witness is the determinant. And trust me, its testimony is about to blow this thing wide open. So here's what the determinant tells us. And it's pretty straightforward. If that determinant is not 0, boom, case closed. We have exactly one unique solution. But if the determinant is 0, well, that's when things get really interesting. That's when we might have no solution at all, or maybe even an infinite number of them. So our first job is obvious. We need to find the values of a that make our star witness say 0.
And that brings us right to our next step, identifying the suspects. Who are they? They're the exact values of a that make our determinant equal 0. These are the troublemakers.
So how do we find them? It's a pretty standard 4-step process. First, we'll pull all the coefficients into a matrix. Then we'll calculate the determinant. You know, the usual way. Step 3, we simplify the expression we get. And then, the most important part, step 4. We set that whole thing equal to 0. But remember, we're doing it in our z sub 7 world. So after we run the numbers, do all the math, this is what it boils down to. Our determinant is this really nice, clean, factored expression. This little formula right here, this holds the key to the whole mystery. Okay, time to set the trap. We take our formula and we ask the million-dollar question. Which values of a make this whole thing equal to 0 in z sub 7? This is exactly how we're going to catch our suspects. And bingo, we got them. Our 2 prime suspects are a equals 1 and a equals 5. Now, a is pretty obvious, right? If you plug in 1, that first part becomes 0. But why 5? Think about our 7-hour clock. If a is 5, then a plus 2 is 7. And in z sub 7, 7 is the same as 0. So that makes the whole thing 0 too. For any other value of a, the determinant is not 0, which means we get a nice, simple, unique solution. All right, we've got our suspects in the interrogation room. A equals 1 and a equals 5. Now it's time to grill them. We need to plug each one back into the system and see exactly what happens. Do we get no solution? Do we get tons of solutions? Let's find out.
And here's the summary of our findings. This is pretty wild. For our first suspect, a equals 1, something crazy happens. All 3 equations basically become the same thing. So we have way more freedom. In fact, we end up with 7 times 7, that's 49 different solutions. But for our second suspect, a equals 5, the opposite happens. The equations start contradicting each other. It's like trying to prove that 0 equals 3. It's impossible. And that means for a equals 5, there is no solution. None.
Okay, We've gathered all the evidence. We've interrogated the suspects. We know exactly what happens and when. It is time to deliver the verdict. Let's review the options from the very beginning. Option A, is there a unique solution for every value of A? Nope, that's false. We know A equals 1 and A equals 5 are exceptions. Option C, is there an A with 7 solutions? False again. We found one with 49. D, 14 solutions? Also false. Well, by process of elimination, that only leaves one option standing. The mystery is officially solved. The one true statement is B. There does exist a value of A, specifically A equals 5, where the system has absolutely no solution. Our investigation proves it. Case closed. So, we've cracked this case. But, every solved mystery just opens the door to a new one, doesn't it? What if we changed the rules? What if instead of a 7-hour clock, we were working in Z sub 5, a 5-hour clock world? Would our suspects 1 and 5 even be the same? Would the whole outcome change? That's a case for another day. Thanks for joining the investigation.